I've loaded up Paraview, so we want to look at our results. So here's I said open. I clicked up on the upper left to open. On the lower left of the dialog window gives me my recent directories. And so I'm going to double click on output to get my most recent directories. I'm going to look at the solution of the entire domain. And so that was step03.vtk. The VTK writer will put in the timestamp. This is just the convention that VTK files uses and Paraview expects. So I click on that file, hit OK. I now have to, you'll notice that this apply button is highlighted. And so I need to apply it to actually load the data in. Now I have a cube. You can see my orientation axes on the lower left. So I rotated. This is my box. So up here it says solid color, so it's just showing the solid color. I'm going to show the displacement field, so I switch down to displacement. There's a default color map. By default, it's showing the magnitude of displacement, and it's going to show it on the surface. I can select wireframe to just show the wireframe. Surface with edges shows the surface plus the edges of the cells. And this color scheme with the white in the middle and blue and red is best for divergence. So I'm going to switch from displacement magnitude to the y component of the displacement. Now my Dirichlet boundary conditions on the right side and the left side are shown in white, and I can clearly see the discontinuity in the displacement field across the fault. There's a couple very handy things if I want to visualize the deformation. I can click on this little warping icon right here, warp by vector. And the default is the scale factor of 1. And I'm going to increase this to 500. So it's going to exaggerate the deformation by a factor of 500. And so there's the deformation. I have a question. So PyLith decomposed displacements into XY components. So PyLith wrote out the displacement vector, all three components, X, Y, and Z. And then here within Paraview, I can either choose to display the magnitude of that displacement vector or each component individually. And so I selected here within Paraview the Y component. I could have selected the Z component or the X component. And notice my color bar will actually update itself automatically depending on which component that I select. So I see that there's a Trelis question. I'll come back to that after I show a couple more things in Paraview. So the other thing that you often want to do is you often want to show the displacement field as a function of arrows. So this is using the glyph button right here, a little globe with some dots on it. Looks like a little bit like satellites hovering around a planet. So glyph type, I'm going to do arrows. I'm going to show the displacement field. I'm going to scale them according to the vector scale factor. I'll match my scale factor of 500. Glyph mode, I went all points. And I'll hit apply. So now here are, and those are showing, notice that when I did my displacement, when I selected the glyph, I was selecting my original configuration. And so when it plotted the points, it plotted them from the original configuration, and it's showing the deviation to the current warped configuration. So the arrows start at where my original mesh was, and they point to the location of where that vertex is in the deformed configuration. So here along the fault, originally both sides of the fault were at this point here. and then the right side moved up here, and the left side moved down there. And so you can see I have indeed left lateral displacement across the faults. And if I zoom in, you can see that there's a little bit of reverse deformation. And if I look at the side view here, you'll see that I had uniform horizontal slip over the top 2 kilometers, and then it tapers linearly to 0 at depth. And you'll notice from the top view, because I've exaggerated the deformation by a factor of 500, it looks like the volumes have interpenetrated each other. If I didn't exaggerate the deformation, things would be lined up. Also, PyLith uses the original configuration of where the fault surface was in the undeformed configuration. So all the motion is lateral using that original geometry. If I can turn these off using the little eyeball icon over there on the right. If I want to look at what my fault surface is, I can bring up and load the fault in here. So again, I hit apply. Here's my fault surface. And I toggle there in 3D. So now let's say I want to put my domain in there. I'll do a wireframe view. And so this is my warped wireframe view. Let's actually go back. Let's turn off the warp configuration. I want to see my original configuration. So there's the fault surface. And on the fault surface, let's display the slip magnitude. Here it says X, Y, and Z. These are not X, Y, and Z components, but these are the left lateral, reverse, and opening components. So if I select the opening component, notice that, and let me go back to solid view so I have just the slip color bar showing. So you notice that my slip, everything is dark blue, that's 0 slip, so my fault opening is 0. Let's go back to fault X component, which is actually the left lateral component. You'll notice that here you can see that it's uniform value of 2 over the top 2 kilometers, and then it tapers linearly down to 0 at the bottom. So I can see that the slip distribution matches what I expected to be input. And so I can turn off that fault. Another thing that you can do, without a time-dependent problem, it's not that useful, but you can actually, within, if you want information about a point, you can select this little icon up here. Sorry, it's a little small, but it's a little square with the red dots in it, and I can select a point here, and I can see the information. And so up here, there's various icons like plot selection over time. If I click on that, it's going to split my window. Sorry, I have to hit apply over here. So it says I'm going to copy the active selection. No time steps and input data. So it didn't like that, but you can see that it split my window into 2, and so it's going to do a time series over here on the right. So that allows you to interact with your data and look at multiple things. So I had a question, slip occurred only along a portion of the fault if at bottom is 0. So yes, so you'll notice that the slip in here along the bottom of the domain is 0, and then it was, so if I turn on my warped, let me go back to solid. Let me turn off turn off the fault. So there you can see the slip that I had is 0 at the bottom. So if I look at the bottom of the domain, you notice that there was 0 slip. And as I get near the surface, it's 2 meters horizontal. I did a 1/4 meter vertical. And then I had at halfway down the domain, I tapered I had 0 vertical slip, and then I tapered that linearly down to 0 at the bottom. I could have, this may be something you want to try, you add in and change the value that I had here in the spatial database for 2 kilometers depth. I could have made this 0, and then that would have locked the fault below a depth of 2 kilometers and had only slip in the top half. So you don't have to prescribe slip everywhere on the fault surface. In this case, I have a through-going fault, so I can, do the whole offset 2 blocks and attend and have actually accumulation of slip across the fault surface to continue to form and translate these blocks past each other. Okay, so getting back to Farouk's Trelis question, to model multiple fractures in a 3D body, do we need to define multiple volume as a surface of discontinuity, a single volume without putting fractures between adjacent volumes? So if you're talking about trying to put in multiple sort of slip surfaces within a volume, PyLith is implemented such that it needs a surface on which to describe and create those dislocations. So PyLith needs a surface as input in the mesh. CUBIT, to create an interior surface, it does not know how to create just interior surfaces within a volume. It only knows how to create surfaces that divide 2 volumes. So for the mesh to actually honor any interior surfaces and actually have vertices on those surfaces and be connected so that the topology of the mesh conforms to those interior surfaces, you have to have those surfaces splitting through the volume. So just in the same way that we divided our single block into 2 blocks for our fault surface, you would need to do the same thing in your volume. Now, if your volume is much larger than your fault surface, then what you do is you need to extend those fault surfaces through the volume. Now, you don't have to go, every surface does not have to extend to the outer boundaries. So for example, in this case here, if we had, say we wanted a T-intersection of our fault, we could have had this original fault, through-going fault in this case, but then in CUBIT, we could have, if we wanted a T-intersection on, say, this block on the right with a fault coming out perpendicularly, we would have just split the right block. And so we would have a fault running through the middle of this right block, but our fault surface would not have to extend into the other block when we did set up our geometry. So once I had this volume on the right, my fault surface, I can split just the portion of it. Now, when you go into 3D with very complicated surfaces, sometimes you may want to sort of put in some additional artificial boundaries. So I have put in things like a horizontal boundary, that's down about the depth of the mantle, maybe a little deeper, just so I cut off my fault surfaces and they didn't extend all the way down, because I had multiple fault surfaces that intersected at very odd, difficult angles. In some cases, they were very convoluted shapes that were hard to mesh, and CUBIT would often just fail to mesh. And so I end up deciding to create an artificial horizontal boundary that ran through my entire domain, and then my fault surfaces were truncated at that boundary at depth. And so that is one option. Sometimes it's easier to extend them horizontally or vertically and not horizontally. It all depends on your geometry, how many faults you have, and what they are. But PyLith does rely on the fault surfaces have to be prescribed in the geometry of the mesh. We are looking forward to implementing so for Green's functions, we like to implement something with point sources that would allow you to not have to specify. You would specify the fault as a function of, as a collection of point sources rather than an actual continuous surface. But there's difficulties in that as well, as certain terms of convergence and dislocations and the accuracy, in terms of the deformation as you're getting close to those. So we're pretty much ready to wrap up this first session. Are there any additional questions? Feel free to continue as questions come up. You can add them to the Q&A chat window, or sorry, the Q&A window rather than the chat window. I will actually go in and between this session and next session, cut and paste the questions that were put in the chat window and put them in the Q&A window so that then we'll have an archived version of the response. I'll type out the response for those questions. You can also send email to CIG-short, and we can respond through there. Charles will cover in the next session, beginning in about an hour and a half. Between then, I will try and get a link up of where this is recorded, so you can stream back. You can continue to poke around some of the examples, run those. The example that Charles will be covering is discussed in the manual. It's 2D Green's functions. So it's in examples 2D Green's functions. I don't know whether he'll pick the strike slip example or the reverse example. So we look forward to seeing you in about an hour and a half for session number 2. And don't be afraid to enter in more questions in the Q&A window. And we'll look forward to seeing you then.